Thank you.
All right, thank you again for the kind invitation and the kind introduction. I'm very happy to join you virtually today to talk about some of the exciting work we are doing in creating new artificial quantum materials. And my talk today is going to be focused on complex oxides and their interfaces where we can, and I'm going to talk about how we can combine these materials with different physical properties to create sharp interfaces where emergent phenomena can happen. So I'll be talking about how we can use synchrotron-based techniques to characterize the structures and properties of these materials at the atomic scale, and combine our synthesis capabilities to develop materials with new interesting properties. Before I start, I'd like to acknowledge my research group, my grad students and postdoc, and collaborators at national labs and over here at NC State and elsewhere who have contributed in many ways to the work I'm going to be describing. All right, so there are a wide range of interesting quantum materials and a lot of 2D materials, which a lot of good work has been done on in trying to control their properties. I'll be focusing on a class of materials known as the transition metal complex oxides, which have a perovskite crystal structure. So these materials have a transition metal ion indicated by this blue atom here, which sits in the center of an octahedron of oxygens, which are these red atoms in the structure. And at the green sides are other metal ions, which could be the rare ions or group 1, group 2 ions. And in these systems, we can control the physical properties by changing the chemistry. For example, if we have titanium in the center of the octahedra and barium or lead at the corners, we have a material which is insulating and ferroelectric. And we can also have materials which are magnetic and materials which are superconducting and materials which also exhibit interesting different other parameters. And so these materials have, a lot of these materials with different chemistries have very similar lattice spacings. And so we can envision combining all these different other parameters when we make thin films of these systems to form interfaces. All right, in addition to changing the chemistry of these materials to change, to realize interesting magnetic and electronic phases, in these systems, there's a strong correlation between the atomic scale structure of these systems and the orbital and electronic and spin degrees of freedom. And so an example in this case is for material like lanthanum manganite, where you have lanthanum at the corners as these green atoms and manganese 3+ ions in the center of the octahedron. If the system is in the cubic phase, then due to the coordination with these oxygens here, there is a crystal field splitting, which splits the d orbitals into a lower energy T2G manifold and a higher energy EG manifold. And in the system here, the manganese has 4 electrons in its d shell, and those electrons will fill these shells following Hund's coupling. And we can also change the number of electrons in the system by doping at the green atomic site in this system. We can apply pressure to this material to move it from a cubic symmetry to a tetragonal symmetry, for instance. So in this cartoon here, I'm showing what happens if you apply pressure, biaxial in-plane pressure to reduce the bond lengths in plane and elongate the bonds in the out of plane in the z direction. And what this effectively does is it breaks the degeneracy of the orbitals, the EG orbitals, and the in-plane line orbitals end up with a higher energy than the out-of-plane pointing orbitals. And so this ability to apply pressure to these systems also allows you to change the relative energies of these orbitals with implications for how these materials order their spins and what the electronic properties of these systems end up being. So in these systems with different compositions and slightly different structures, we can envision, again, creating new emergent electromagnetic phases by combining systems, these transition metal oxide perovskites, with different other parameters in thin film form. And if we grow these materials as thin films, we can use strain engineering to effectively change the relative bonding of the atoms in these systems to change their properties. Or we can also create multi-layer structures shown in this cartoon here, where the different colors here represent different perovskite oxides with different physical properties. And what I'm going to show in my talk today is that this ability to engineer the interfaces of these systems and use strain engineering can lead to unique coupling of these spin, charge, and orbital degrees of freedom to realize very interesting physical properties. All right, so in addition to using strain and creating multi-layers where you couple the properties of these systems, one other degree of freedom we have in these systems when we grow them as thin films is to control the electrostatic boundary conditions of these films. And a very common example of one system where these electrostatic boundary conditions can lead to very interesting properties is the case of lanthanum aluminate grown on strontium titanate. So if you grow films of lanthanum aluminate along, in this cartoon here, the 001 direction on a strontium titanate substrate, both of these materials are band insulators in their bulk form. And the lanthanum aluminate, if we consider the ionic limit of this system, can be considered to be a polar material. So you can see here that if you consider the formal charges of lanthanum and oxygen and aluminum and oxide oxygens in the layers here, you can think of lanthanum aluminate as being alternate layers of this positive and negatively charged layers along the 001 direction. At the interface with the strontium titanate, which has neutrally charged planes just from considering the formal charges of strontium and titanium, you can see that there's a polar discontinuity where you're going from a neutral charged titanium dioxide plane to a lanthanum oxide plane. And depending on the surface termination, you can either have a positively charged lanthanum oxide surface or a negatively charged aluminum dioxide surface. In these systems, the polar discontinuity here can lead to what is known as a polar catastrophe. And if you calculate what the potential should be if this interface is atomically sharp, what you find out is that the electrostatic potential diverges as you increase the thickness of this lanthanum aluminate film, which the system tries to avoid. And there are a couple of mechanisms by which this interface can reconstruct to avoid this what is known as a polar catastrophe, this divergence of the electrostatic potential. One of the mechanisms proposed involves the transfer of charge from the film to the interface. Another thing that can happen is that you can have ionic intermixing where some of the trivalent charge here can move across that interface to replace and get exchanged with some of the strontium, the divalent strontium ions. And the other thing that can happen is that you can have structural rearrangement where some of these layers here can polarize or can form intralayer dipoles in response to this interfacial polar discontinuity. The effect of all these is that we have these two relatively boring materials which reconstruct to avoid this polar discontinuity. And what's interesting here is that these reconstructions lead to an interface here which exhibits a high mobility two-dimensional electron gas. And because this electron gas is confined at this interface, there's breaking symmetry along the z direction, and that leads to a Rashba split of the electronic states inside of this two-dimensional electron gas. And people have discovered that this 2-deg, which forms at this interface, also has some signatures of ferromagnetism and low temperature superconductivity. And so this is an example of where you have these emergent properties which arise due to the relaxations of the electrostatic boundary conditions inside this LAO-STO system. In addition to this, to charge transfer and the emergence of these really interesting properties, one thing that can also happen at these interfaces is that due to the electric fields which arise here, you can also have changes to the atomic scale structure of these systems. And so in the LAO-STO case, there's been theoretical proposals and some experimental evidence to support this, that the electric field at the interface here can lead to a round plane of the cations and anions. And so in bulk LAO, for instance, even though you have rotations of the oxygen octahedra, on average, within each of these layers, the oxygen and the cations occupy the same average Z position. As a result of this polar discontinuity, one thing that can arise is that you can have a rumpling of these bonds here. So you can see in this situation here, the oxygens are moving down relative to the cations in the layers which are close to the interface. So one can envision using this approach of tuning the electrostatic boundary conditions to also change the atomic scale structure of these transition metal complex oxide systems. All right, so the interest of oxides in quantum materials is that we have all these different degrees of freedom which we can tune, and the hope is that we can create all oxide devices where we can take advantage of these functional properties for a wide range of applications, from memory to sensing to quantum computation. And I'm going to focus in my talk today on talking about what happens in some of these systems with polar discontinuities. And I'm going to talk about how these polar discontinuities and the changes in structure can lead to very interesting magnetic and electronic ground states. The first system I'm going to focus on is lanthanum strontium manganite, which is a ferromagnetic metal when you have 30% strontium and 70% lanthanum at room temperature. And what I'm going to show is that by understanding the structural distortions which occur at these interfaces with lanthanum strontium manganite and other oxide systems, we can stabilize magnetization in atomically thin LSMO films. And then I also show that we can tune this magnetization by coupling the LSMO films with ferroelectric oxides like lead zirconia titanate, where this coupling of the ferroelectric order parameter and the magnetism in the LSMO can lead to non-volatile switching of magnetization in these systems. And then I'll talk about how we can also stabilize a two-dimensional electron gas at a different polar-nonpolar interface. And in this case, I'm going to be talking about the anti-ferromagnetic lanthanum chromate system and the steps we can take to also create a two-dimensional high-mobility electron gas at the interface with strontium titanate, and show that we can achieve efficient spin-to-charge conversion inside of this two-deck LCO-STO two-deck. And this is just a picture of the chromate STO and the two-deck which forms at the interface. All right, so in this whole talk, I'm going to be showing that we can grow these materials with atomic precision using molecular beam epitaxy, which allows us to very systematically control the interfacial coupling. And I'm going to show that we can probe these interfaces, these buried interfaces, using a wide range of techniques, including synchrotron X-ray diffraction and high-resolution electron microscopy, to really understand the structure property relations in these ultra-thin quantum materials. And then I'm going to show that the understanding of these materials and the combination with first principles theory allows us to design new interfaces with very specific functional properties. All right, so in my lab here at NC State, we are growing these thin oxide films using oxide molecular beam epitaxy, which allows us to grow these oxides with atomic scale precision. And so this is a slow growth technique where we are growing these films one atomic layer at a time with typical growth rates of an atomic layer per minute. And this slow growth rate in this ultra high vacuum environment allows us to grow these materials with good control of the stoichiometry of the films and to achieve atomically abrupt interfaces. And the growth in these under these conditions also is compatible with commercial semiconductors. And so there's the ability to transfer all these interesting heterostructures we are growing to established semiconductor technologies for device applications. So this image here shows in situ electron diffraction we can perform during the growth of these thin films, where we can monitor the film crystallinity as we are growing them, and also monitor the film thickness by monitoring the intensities of these diffraction images. This high-resolution transmission electron microscope shows a system we've grown, where we've grown a chromate and manganite, where the chromate layers are grown to be nominally 2 unit cells thick, and the manganite layers are grown to be nominally 3 unit cells thick. And from this high-resolution electron microscope image, you can see clearly that we're able to achieve very well-defined layers of this chromate separated from these manganite layers. And I'm going to talk about why we go this particular system and how it leads to changes in the magnetic properties of these ultra-thin films. All right, so in addition to being able to grow these films, we have to be able to image the atomic scale structure. And one way we can do that is using high-resolution electron microscopy. But in addition to that, we also are interested in getting three-dimensional information about the atomic scale structure and layer-resolved information about the spin and the electronic properties of these systems. And so some of these experiments we are performing done at the Advanced Light Source at the LB, Lawrence Berkeley National Lab, and at the Advanced Photon Source at the Argonne National Lab. And the synchrotron X-ray technique we're using to image the structures is a technique where we are measuring along what are known as crystal truncation rods. And in this experiment, what we are doing is we are trying to sample 3 dimensions in reciprocal space of our thin films, which are grown epitaxially on a bulk 3-dimensional crystal substrate. And along these directions known as crystal truncation rods, because the film here breaks the periodicity of the crystal along the growth direction, we get intensities in reciprocal space along the Z direction, QZ direction in reciprocal space. And these intensities contain all the information about the film structure and the surface and interfaces it forms with the substrate. And so being able to measure all these intensities in 3 dimensions and being able to determine and reconstruct the phases associated with all these intensities allows us to reconstruct the real space 3-dimensional structures of these very thin films and their interfaces. All right, so I will not go through much into the analysis technique, but what it essentially entails is the fact that the intensities we measure along these crystal truncation rods are intensities which come from a coherent sum of scattering from a thin film, surface, and interface, and a bulk substrate. And the intensities we are measuring are the absolute square of the sum of these structure factors, which are complex values. And so in an X-ray diffraction measurement, you get these intensities, but you lose information about the phases associated with each of these I's of Q's. And the challenge in X-ray crystallography is to reconstruct these phases to be able to go back from reciprocal space to a real space structure. And so to do this, what we do is we make this answer that the scattering from this film, an interface which we do not know, which we like to determine, comes from 2 contributions. So one contribution is a model structure we have for our film, since we know what the thickness is and roughly what the composition should be, and some perturbation delta S of Q. And by treating this iteratively, we can converge on a structure S of Q here, which minimizes this perturbation by imposing constraints in real space and reciprocal space. And the end result of this is that once we find the correct phases or the correct delta S of Q, we can perform an inverse Fourier transform to get a 3-dimensional electron density map of our system, which allows us to determine the atomic positions of every single of all the atoms in our material with layer resolution, and we can resolve the positions of all these atoms here with sub-angstrom resolution. And I'm going to show that this sub-angstrom resolution is really critical for really understanding the changes in the magnetic and electronic properties of these transition metal oxides. All right, and the intensities you see here are proportional to the atomic numbers, and so just like in a high-resolution electron microscope image here, we can determine the chemical profiles in these systems from the intensities of these atomic locations in the unit cell. All right, so we've applied this technique to study a wide range of systems. We've looked at quantum dots grown by droplet heteroepitaxy technique. And this COBRA technique allows us to resolve the chemical and strain profiles of these quantum dots with layer resolution. We've performed some recent work in looking at some of these complex oxide materials where we can tune the interfacial carrier densities by changing the amount of oxygen in these systems. And here we're able to resolve the atomic positions, again, with sub-angstrom resolution. And what we find in these materials is that there's a strong correlation between atomic displacements, and in this case, the distance between, in the z direction, the polar distortions which occur in these materials, where there's displacement of the oxygens relative to the cations. And this distortions we find are very strongly dependent on the sheet carrier concentrations of these systems. And so I'm going to talk more about this LCO-STO system and how we can understand how the correlation between these polar distortions and the carrier, sheet carrier concentration in the two-dimensional electron gases which form at this particular interface. All right, so polar discontinuities I've shown can, the relaxation of these polar discontinuities can lead to very interesting changes in the interface structure and composition. And so it presents a new route to tune the functionality of materials. And so what I would like to answer now is whether we can use these polar discontinuities to tune not only the structure of thin oxide films, but also their functionality. And I'm going to first talk about how we can understand thickness-dependent properties in some of these complex oxide materials, particularly focusing on magnetic transitions in lanthanum, strontium, manganite. So lanthanum, strontium, manganite, or LSMO, is a very important transition metal oxide because you can tune the magnetic and electronic ground states in this system by changing the relative amount of the trivalent lanthanum and the divalent strontium in the system. So adding more strontium to the system increases the number of holes, and that changes the relative amount of manganese 3+ and manganese 4+ ions in the system. And the interest here is that by tuning the composition, which effectively also tunes the structure, you can achieve a wide range of electronic and magnetic ground states in the LSMO system. One particular composition which we're interested in is a 30% strontium doping, where there is a transition from a paramagnetic state into a ferromagnetic state at a temperature of about 350 to 370 Kelvin, which is above room temperature. And the system is very interesting because it has it exhibits a colossal magnetoresistance and is a spin polarized half metal with applications in spintronic devices and for non-volatile memory applications. So this material is really has been studied a lot in the bulk form to understand the structure property relationships. And what we like to do is understand what happens if you take this material in its bulk form and reduce its thickness along one dimension into a thin film. And also what happens when you create an interface between these very thin layers of LSMO and other oxide systems. So we want to know what happens to the structures of these systems and also how their physical properties change as a result of this reduction in the dimensions and the creation of interfaces. All right, so if we have a very thick LSMO film, which we can grow, well, for us, thick is on the order of a few tens of nanometers. If you have a 12 nanometer thick LSMO film grown on strontium titanate along the 001 direction, what we find is that if we measure the magnetization as a function of temperature, there's a transition from a paramagnetic state to a ferromagnetic state at about 330 Kelvin. And this is very close to what you expect for bulk, which tells us that the material for these thicknesses are behaving very similarly to what the bulk should exhibit as far as the magnetic properties are concerned. However, if we grow these materials and we reduce the thickness of the LSMO by a factor of 10 and grow, for example, a 3-unit cell thick LSMO film, what we find is that the magnetization is strongly suppressed and the material becomes highly insulating. Right. And so this thickness-dependent transition is not something that's new in our lab. It's been observed, it's been known for a while, and has been referred to as the dead layer effects in LSMO. And I should point out that dead layer effects are also known in a wide variety of other oxide systems where there is some thickness-dependent transition. And so from a transport point of view, if your thin films are if your LSMO is relatively thick, 13 to 70 unit cells, the material has a low resistivity at room temperature and it's metallic down to low temperatures. However, if the film thickness is less than 10 unit cells in this case, you can see that there's an increase in the resistivity and the ground state of these materials are highly insulating. From the magnetization point of view, there's also very thick films exhibit bulk-like ferromagnetic properties, But as the thickness is reduced down below about 5 unit cells, the materials lose all their large magnetic moments. So in this situation here, we observe that there is a change in the conductivity and a change in the magnetism in this system, which strongly depends on the thickness of the LSMO film. All right, so we can now look at this system and see what kind of interface it forms when we go it on STO. And if we consider the formal charges of lanthanum, strontium, and manganese for a 30% doping of the LSMO, what we see is that the LSMO is very similar in this sense to lanthanum aluminate, in that the layers here can be also considered to be polar, where you have a negatively charged manganese oxide layer and a positively charged lanthanum strontium oxide layer. And at the interface with the STO, which is charge neutral in its along this given direction, there is also a polar interface, which is similar to the LAO-STO interface, and a polar surface if we terminate these films with manganese oxide. And so we expect there to be reconstructions similar to the LAO-STO case, which might change the local interface structures of the LSMO, not only at the interface, but also at the free surface, where we have this polar discontinuity going from a negatively charged surface to what we'll assume to be vacuum. So we've measured the atomic scale structure of very thin LSMO films. And so this shows the data we get from analyzing the structure of a 10 unit cell thick lanthanum strontium manganite film grown on strontium titanate. And in this case, what we can do is we can resolve in every single unit cell going from the surface to the interface with the STO, the atomic positions and the composition profiles in this system. So this data shows, so what we find is that at the surface of these films, if we look at the topmost surface where we have a manganese oxide termination, what we find is that the manganese ions, these blue ions here, are displaced upwards relative to the oxygen sublattice. And we can quantify this displacement along the Z direction by this parameter delta. And we can measure the delta for every single layer inside of this LSMO film, going from the top layer all the way down to the strontium titanate interface. And what we find is that this this ramp plane is very large at the surface. So it's about between a 1/10 to 2/10 of an angstrom right at the surface of the LSMO film. And as you go away from the interface towards the STO, this distortion reduces to 0. And as you go down towards the interface with the strontium titanate, we find that the distortion starts to increase again as we get closer to the STO substrate. One other thing we can also measure is the unit cell size. And so what we find is that the unit cell of the LSMO is expanded at the surface in the top 1 to 2 unit cells, and also expanded as we get towards the interface with the strontium titanate. And there's also a slight expansion in the STO itself at the STO layer very close to this interface. Additionally, we find that there is an intermixing. So there's a little bit of strontium, which goes from the substrate to the film, and a little bit of lanthanum, which goes across that interface. And so all of these distortions here are very similar to what is seen in the LAO-STO case. And so we would like to now examine how these distortions might be responsible for the thickness-dependent changes in the magnetic and transport properties of LSMO. All right, so one thing I haven't mentioned is that in these materials, a lot of the interesting physics is dictated by the bonding or the hybridization of the oxygen p orbitals and the neighboring manganese or the transition metal ion d orbitals. And so in this particular situation where we have this polar distortion where the oxygens are moving down relative to the manganese, what we are essentially doing is we are increasing the bond distance between manganese and oxygens, and also decreasing the angle of the bond angle, the manganese oxygen manganese bond angle away from the optimum, which in this particular system should be about 165 degrees. And a consequence of this distortion of the bonds is that you reduce the orbital overlap or the hybridization of the manganese and the oxygen p orbitals. And the reduction in this hybridization reduces the hopping of charge and also the ferromagnetic ordering in this system. And so we think that these structural distortions we observe here are the reason why very thin layers of LSMO tend to be, or part of the reason why very thin layers of LSMO tend to no longer be ferromagnetic. And that has to do with the fact that we are reducing the hybridization of the manganese and the oxygen p orbitals due to these structural distortions. If we go a few layers below the surface, so the decay length of these distortions are about 2 to 3 unit cells. If we look at the layers in the interior of the LSMO, we can see that there are no distortions, and the composition is what we expect from our growth conditions. And the octahedral rotations we can also measure very precisely from these X-ray diffraction measurements. And what we find is that these interior layers have very bulk-like structures. And so we expect that these layers here should be more ferromagnetic and more conducting than the layers of the surface and the interface. So the general picture we get here is that if you have a very thin LSMO film where the thickness is on the order of 4 to 5 unit cells or less, the structure is going to be dominated by these surface distortions and interfacial distortions. And the change in the composition and structure here will lead to changes to a paramagnetic insulating state. And as you increase your film thickness, you're going to get layers in between these two regions, which have bulk-like, which are far enough from the surface and interface that you have a bulk-like structure. And this is correlated with the emergence of a ferromagnetic metallic state as you increase the LSMO film thickness. All right, so one way to suppress this, so in addition to the changes in structure and the changes in the composition, it's also been found that you also get electron charge transfer at the interfaces between the STO and the LSMO films, and this has been resolved using electron energy loss spectroscopy, which is and so one approach to suppress this charge transfer and to suppress all these distortions which can occur at these interfaces is to try to insert some layer of this LSMO interface to suppress the changes or to suppress the polar discontinuity. So one approach here has been to put a layer of, for example, lanthanum strontium with a slightly strontium, with more strontium than lanthanum, with a different composition from your LSMO film. And if you have the right composition of this single layer that you can insert at this interface, what is shown here is that you can avoid this divergence of the electrostatic potential. And what has been shown from electron microscope is that measurements is that this insertion of this lanthanum strontium layer at this interface with a different composition can lead to sharper, more atomically abrupt interfaces. And this has been correlated with an increase in the magnetic properties of these thin LSMO films. All right, so being able to insert these layers, these atomic layers, can have a very large impact on the physical properties of these systems by modulating the electrostatic boundary conditions of these thin films. All right, so what we're going to do is so this study, for this particular study, had the thinnest film, ferromagnetic film, being 5 unit cells, and we wanted to see if we could push this critical thickness even further down to lower LSMO thicknesses. So a 2 unit cell thick LSMO film is not ferromagnetic, and so it's magnetically dead. And what we like to do is modify the surface and the top surface and the bottom interface here with some other material here, which will have the same charge stacking as the LSMO, such that there is no electric field at this top interface and the bottom interface. And the material we chose to do this with is lanthanum strontium chromate. So lanthanum strontium chromate is a G-type antiferromagnet in bulk for 30% strontium doping. It's insulating. And if the composition stays as you want it to be, then you expect there to be the same plus minus 0.7 charge stacking in the chromate layer as there is in the LSMO layer. So effectively, if there is no charge transfer at this interface, then which might shift the relative charges of this chromate and manganite sublattices, then you expect the polar discontinuity to be alleviated at the LSMO top and bottom interfaces. So we've been able to grow this material using molecular beam epitaxy, and the films are atomically smooth on the surface. The reed shows diffraction spots, which is indicative of 2-dimensional growth. And the reason we chose lanthanum strontium chromate is that we can tune the lanthanum strontium ratio to make it balance match with the LSMO layer, such that we have no electric field at the interface. And because the lattice constant of LSCO is very close to that of LSMO, we expect there to be no additional strain which is introduced into these heterostructures. Additionally, the LSMO and LSCO have very similar octahedral rotational patterns, which means that the interface we form between these two materials is not going to significantly distort the octahedral rotations inside of the LSMO away from what the optimum rotations should be. And the other thing that we found is that the chromium, compared to other transition metal ions like iron, so for example, if you were to put lanthanum strontium ferrite at that interface, even though it might be valence matched, there is a large electron charge transfer between iron and manganese at that interface, which can dope your LSMO from your optimum doping. So in this particular case, we can suppress this charge transfer. We find that this charge transfer is suppressed at the LSCO, LSMO interfaces. All right, so the first thing I'm going to talk about is what happens to the atomic scale structure of these very thin films when we add the chromate layers on the top and bottom interfaces. And to do that, we took the samples back to the Advanced Photon Source at the Argonne National Lab and measured diffraction along the crystal truncation rods for a 4-unit cell thick LSMO film and a 4-unit cell thick LSMO film with the chromate on the top and bottom interfaces. And so what I'm plotting here, what I'm showing up here is the a slice through the 3-dimensional electron density map, which shows the manganese atoms and the titanium atoms in the strontium titanate, and the oxygens in the planes of the MnO2 and the lanthanum strontium oxide layers. And so what we find is that if we have just an LSMO film going on strontium titanate, you can see that the charge density of the manganese here is shifted upwards related to the oxygen charge density. Again, we can parameterize this displacements by this delta parameter here, and we see that this delta here is very large at the surface, and it decays as you go below the surface and increases again, just like we saw in the 10-unit cell thick LSMO film. Now, if you encapsulate this LSMO film with a chromate on the top and bottom interfaces, so here we have our LSMO layers and the chromium on this side and the chromate on the other side, we can see that the surface chromium oxide layers have the strong polar ramplings. However, the manganese oxide layers here have the oxygens in the same along the same Z position as the oxygens. And so in the LSMO layers where we have the chromate on both sides, we can suppress the polar distortions and the manganites, which is what we care about in this case. And we've also measured the octahedral rotations, and we find out that the octahedral rotations are what we should expect for bulk LSMO. All right, so here for a 2-unit cell thick LSMO film, we find out that the structure should be strongly distorted, explaining why it's not ferromagnetic. And now if we take our LSMO film and we put the chromate on either side of this film, we find out that we now have a finite magnetization measured using SQUID. And in this particular case, for a 2-unit cell thick LSMO film, we observe this evidence for ferromagnetic ordering. And this is achieved here by the fact that we are controlling the interfacial structure of these systems by inserting these lanthanum strontium chromate layers. All right, but one thing, so the main big result here is that a 2-unit cell thick film of LSMO by itself is not ferromagnetic. We add the chromate and we end up with some ferromagnetism, which is not as large as we should expect for bulk. But what we find is that if we keep the chromate layer thickness fixed and we measure the magnetization of samples where we vary the LSMO thickness from 2-unit cells to 10-unit cells, we find out that the Curie temperature increases as we increase the LSMO thickness, and the saturation magnetization also increases as we increase this LSMO thickness. So what we find in here is that the total moment of these systems depends on the LSMO thickness. And what we found is that it more importantly depends on the ratio of the lanthanum strontium manganite to the lanthanum strontium chromate thickness. So this implies that either two things, either the LSMO is, even though we have a bulk structure, there might be some changes in the spin orientation with the film thickness, or there could also be some contribution to the total magnetization coming from the lanthanum strontium chromate spacer layers. So we expect there to be, initially expected the LSCO to be anti-ferromagnetic and have no net moment. But this thickness dependence we're observing here implies that there might be some correlation between chromate thickness and the LSMO thickness. So to be able to quantify or to probe the magnetization in the chromate and manganite sublattices separately, we use X-ray magnetic circular dichroism, where we can, using a circularly polarized X-ray beam, excite electronic transitions from the transition metal ion occupied 2p states into the unoccupied 3D density of states. And so if using a circularly polarized light, we can use left and right circularly polarized light to find the difference in the density of states, unoccupied density of states of the states with up and down spin orientations. Right, and so what we've, in this experiment here, we apply a magnetic field in plane to the LSMO system. And at the manganese L edge here, we are probing the excitations of, we probing the magnetism inside the LSMO sublattice of the system. And so in this system here, where we have 3 unit cells of LSMO with 3 unit cells of the chromate on either side, we find this difference in the absorption for the left and right circularly polarized light, which I'm plotting down here, which implies that the LSMO film, even at 3 unit cells here, is ferromagnetic. That is, the spins in the LSMO are aligned in the same direction as the applied magnetic field on average. At the chromium edge, where we expected no dichroism, what we found was that there was a dichroism. So the left and right circularly polarized light showed a difference. And this difference, if integrated, was negative, which implied that the chromate spins were aligned anti-parallel to the applied magnetic field. So what the model we get from this X-ray magnetic circular dichroism is that rather than just the LSMO being ferromagnetic, you also have spins in the chromate layers which are anti-parallel to the applied field. And we can measure at the L edges of the chromate and manganese the XMCD signals and monitor this as a function of the applied field and to obtain these hysteresis loops. And what we find is that the hysteresis loop for the manganite at the manganite L3 edge is if we overlap that with the negative of the chromate. Remember, the chromium has spins in the opposite direction. So if we flip this and overlap the two, we can see that they follow each other exactly, which tells us that the magnetization inside of the manganite layer is controlling the spin orientation inside the chromate layers due to an anti-ferromagnetic exchange between chromium and manganese across this hetero interface. All right, so this explains why we should have this thickness dependence. It has to do with the fact that we have the chromate, which is contributing about -2 Bohr magneton per chromium to the total magnetization. And as we increase the LSMO thickness, we're effectively increasing this positive contribution, which leads to this increase in both the saturation and the Curie temperature of this system. All right, so we should really be describing these heterostructures as ferromagnetic systems where we can tune the ferromagnetism by simply controlling the relative thicknesses of the LSMO and LSCO sublattices. And again, we can make superlattices of these systems here where we can tune the total magnetic moment by simply changing the relative thicknesses of the chromate and manganese in this system. We can also play around with epitaxial strain. So on the case of STO, we are applying about 1%, we're imposing about 1% tensile strain on these LSMO films. But we can grow these materials on other substrates like LSAT, where we have close to 0, about a 0.2% compressive strain, and on lanthanum aluminate, where we have about a 2% also compressive strain on the system, and investigate how the magnetic properties will change as a function of the strain. And what we do find is that for very thin LSMO, LSCO bilayer heterostructure, so if you go 2 unit cells of LSMO, 2 unit cells of LSCO, the films are still, both are still ferromagnetic. There's a net moment we can measure for these ultra thin LSMO heterostructures. However, if we double the thickness of the LSMO and keep the LSCO fixed at 2 unit cells, what we find is that there's a large difference in the magnetization, which strongly depends on the epitaxial strain of the system. And so this is more apparent if we plot the saturation magnetization as a function of the LSMO thickness for the different strains. And what we find is that the material with the lowest magnitude of the strain on LSAT gives us the highest magnetization, whereas the material with the highest magnitude of strain on LAO gives us the lowest magnitude of the saturation magnetization. So this dependence of the magnitude of the strain on the magnetization has to do with the fact that in the LSMO system, there's a correlation between the orbital ordering and the applied strain. And so I alluded to this at the beginning of the talk in the Atlanta Manganite case. If you apply compressive strain to the system, which is what happens on LAO, what you're doing is, what effectively happens is that you stabilize a C-type antiferromagnetic ground state. So you can see that the spins are anti-parallel in plane and parallel along the Z direction. And this competes with the ferromagnetic ground state, which occurs in the pseudo-cubic, in the cubic phase of this system, where there's the in-plane and out-of-plane pointing orbitals are degenerate. And if you apply tensile strain, then you have an A-type antiferromagnetism, which also competes with this ferromagnetic order. And so effectively, the magnitude of the strain here increases the amount of the antiferromagnetic faction, which is competing with ferromagnetism. And this explains why the LSMO on LAO gives us the lowest strain. And that has to do with the fact that we have a significant contribution to the total magnetization of this C-type antiferromagnetic component. And we can show using X-ray linear dichroism that indeed we are changing the relative energies of the orbitals. And in this case, this is also consistent with the trends that we observe here, where the A-type is dominant in the LSMO case on STO, and the C-type is dominant in the LAO situation of this system. All right, very quickly, we've also looked at the effect of, also studied the magnetic anisotropy in these systems for these very thin layers. And we've grown these heterostructures on manganese oxide, where there's an 8% lattice mismatch, which leads to a relaxation of these films into their more or less cubic structures. In the cubic phase, we expect there to be a very small magnetic anisotropy. But what we do find for these ultra thin layers is that even though the films are completely relaxed and should be more or less have a cubic magnetocrystalline contribution to the anisotropy, magnetic anisotropy, we find out that the easy axis of these very thin films lies in the in-plane direction. We've also looked at the case of these heterostructures on lanthanum aluminate, where we expect a perpendicular magnetic anisotropy. And we also find there that the in-plane the easy axis seems to lie in plane of these systems. And this points to the antiferromagnetic exchange at these interfaces as being the strongest driving factor in controlling the magnetic anisotropy in this system. And just very quickly, I should point out that we've also grown lead zirconia titanate on these heterostructures. And so we've grown this on an 8-unit cell thick LSMO with 2-unit cells of LSMO. And what we do find is that we can modulate the magnetization in these 8-unit cell thick films, but these changes are only occurring in the layers close to the interface. And what we've been trying to do now, been slowed down by COVID, is to go back down to the 2-unit cell thick regime to see if we can completely switch the magnetism on and off. All right, in the last few minutes, and I'll come to Julia's question in a second, we've also looked at the lanthanum chromate, lanthanum strontium titanate interface, where there's also a polar discontinuity. And the idea here is that we want to take advantage of the magnetic ordering in this system to hopefully couple with the carriers inside the LS, confined in the STO side of the system. And what we do find is that if we grow these materials at under reducing conditions, that's high temperatures and low oxygen pressures, we can induce oxygen vacancies in the entire structure in both the STO and the LCO, which leads to high sheet carrier concentrations. And if we do a post-anneal in oxygen, we can fill up the vacancies in the STO and create just a 2-dimensional electron gas at this interface. And this effect of oxygen is very similar to what has been seen in STO. But one interesting thing here is that if we grow these materials under high oxygen conditions, the films become insulating, and even reducing them and annealing them again doesn't seem to create a 2-deck. One has to grow these materials under reducing conditions to be able to get a 2-deck to form in the first place. All right, and so I'll skip this in the interest of time. But one other thing we've been trying to study is the spin injection into the 2 decks at these LCO, STO interfaces. There's been very interesting work done looking at the LAO-STO interface, where it's been shown that there's a Rashba split in the bands of the Fermi, the bands in the STO due to the confinement. And if you inject a spin current, for example, if you grow a nickel ion, a permalloy layer on top, and you use a ferromagnetic resonance to inject a spin current, there is evidence that the spin current is converted into a charge current via something known as the inverse Rashba-Edelstein effect. And this allows us to characterize the Rashba parameter in this system here, that is the splitting of these parabolic bands. And what we've been doing is trying to repeat this measurement for similar configurations where we add nickel ion to our lanthanum chromate on strontium titanate. So I should just point out quickly here that we can determine this alpha, the Rashba parameter, by taking the ratio of the spin current, the 2D charge current, which we can measure as measuring a bias across the 2DEG, to the three-dimensional spin current we inject. And in the interest of time, we've been able to measure this spin current using ferromagnetic resonances, where we can determine this JS by looking at the differences in the damping factors of this nickel ion lanthanum chromate strontium titanate configuration compared to just the nickel ion itself. And we can measure the charge current again by measuring the voltage across the 2DEG as we inject spins using the FMR signal. So we do find evidence for spin to charge conversion in the system here, and we can, using the mobility we get for our films, we can determine an alpha Rashba coefficient for LCO-STO films, which is on the order of 0.1 EV at room temperature. And so what we're doing now is trying to investigate this. And I should just point out that this is a little bit larger than what has been found for the LAO-STO case, although it's a bit smaller, well, another magnitude smaller than what you get for one of the largest Rashba type material, bismuth tellurium iodide. All right, so so one other thing, so since the LCO, as I mentioned, is anti-ferromagnetic, one other thing we're interested in trying to study is what happens if we can couple the magnetism in the polar oxide with the charge carriers at that interface. And there's been a lot of interesting work recently done using europium oxide, potassium tantalate interfaces, and also interfaces between some of these oxides and lanthanum and strontium titanate, where it's been shown using that there's an anomalous Hall effect, which is indicative of a spin polarization inside of the 2DEG. In our case here, what we like to do is we've grown superlattices of lanthanum chromate and lanthanum manganite, where we do find that these heterostructures turn out to be ferromagnetic. And what we like to do here is grow these materials under the same conditions as we grow for the LCO to get a 2DEG to form this STO interface. But our current results show that the interface in this system is insulating. And this is not surprising. There's been very good work done previously looking at lanthanum manganite STO interfaces, where it's been shown that 2DEG doesn't form at the LMO STO interface because the charge, rather than going to the LCO interface, the STO gets localized in the LMO sublattice. And from our XMCD measurements, we find that in these heterostructures, there is still this anti-parallel configuration of the manganese and the chromate spins, which is what we want to happen. We want the spins in the LCO close to the STO interface to point in the same direction. However, we find that there is evidence for manganese 2+, which indicates, again, that the electrons which should be going to the STO interface get stuck in the manganese layers in these systems. All right, so just to summarize, I hope I've shown you that these polar discontinuities at these interfaces have very important and strong implications on the magnetic and electronic ground states. And using the atom by atom growth capability which we have in an MBE system, we can tune magnetic and electronic ground states in these heterostructures to optimize complex oxides with targeted physical properties. Right, so that is the end of the talk. And if you have any questions, I will be happy to take them now.
Well, thank you very much. A very interesting work you've been doing. We have one question from Julia Mundi to read her note. Thank you for the wonderful talk. Do you happen to measure the polar distortions in the LSMO/STO as a function of lanthanum concentration? Question mark. Do you expect a change between the insulating and metallic LSMO compounds?
So the short question is, right now we've only focused on the 30% composition, and we are planning to do a more systematic study of the polar distortions as a function of the LSMO, so the strontium doping. So no, we've not done that yet. We do expect there to be a reduction in the polar distortions as we go from lanthanum manganite to strontium manganite. And as I guess Julia has already shown previously, there's also a correlation between the amount of charge transfer you can get at these interfaces, which is correlated with the fact that you're effectively reducing the polar discontinuity as you add more strontium to the LSMO system. At this point, we find out that the ultra thin layers, so 2 unit cell thick LSMO films, even though they exhibit ferromagnetism, end up being insulating. And we have a few ideas as to why that might be the case. There's some evidence that there might be a little bit of charge transfer, non-negligible, well, a small amount of charge transfer occurring at these interfaces, which we think might also lead to a change in the electronic structure. And so what we're planning to do now is to change the doping of the LSMO to see if we can get this doping to lead us back into the conducting part of the phase diagram.
Oh, thank you. Other questions? You can either type in the chat or the Q&A box, and we'll take a look. I guess while we're waiting for that, I had Julia, yes, thank you. Very exciting talk. Thank you.
Thanks.
Another question, are you thinking about growing thin layers of topological materials using this technique? I know that's a different thing, but just curious.
Yes, we are. So there have been some proposals that some of these oxides can have topological features, particularly if you grow them along the 1-1-1 direction. And so, yes, we have some other materials we've started to investigate, which, based on theoretical predictions, should potentially exhibit topological features. And so, and hopefully in the next few months, we might have some results which might be of interest to the community. Yeah.
All right, thanks very much. Oh, another question from Dan French Segedin. Has an enhancement in magnetic TC ever been shown in heterostructure compared with bulk?
For this particular system, none that I know of.
Yeah.
Well, so there's been some evidence for an increase in the magnetic moment compared to bulk, and so the magnetization can have anyway. Yes. But the mechanism is still under debate. I don't want to speculate.
Okay.
Speculate now. Yeah.
Okay. Thanks. Any last questions? A few. Okay, if not, thanks so much for your talk. A lot of good things.
All right, thank you very much again. And
thanks.
Bye, thank you.
You're welcome.
Bye-bye.